talk about diffusion with homogeneous reaction. And in order to compare it to the last one where we talked about heterogeneous chemical reaction occurring on the surface of the particle. And so we're going to look now at a case where we have a gas, A, that is well stirred, and it's diffusing into a liquid B that is quiescent, at least for the time being. We'll change that a little later. And this gas A reacts with B to form a binary species AB. And a simple example of that would be carbon dioxide diffusing into or absorbing into something like a basic solution like sodium hydroxide. And so we will treat this as a binary system and assume that the reaction product is present in small amounts, and therefore that the presence of this reaction product has no effect on the mass transfer of A and B. This is a so-called pseudo-binary assumption. And later on, when we develop more general laws of mass transfer, I'm going to show you how to justify this assumption and under what conditions it will be valid and how to test its validity. But this is a very common assumption when you is that the presence of this reaction product does not significantly change the mass transfer characteristics of A and B. And what that means is that as you form this reaction product, it's not significantly changing the diffusion coefficient of A and B through this liquid or changing the temperature due to heat or reaction effects or things of that nature. And so the chemical reaction that we'll consider is A plus B going to AB. And we'll assume that the reaction is first order in A, and this is also a reasonable assumption if you imagine that B, the liquid, is present in large excess and that only a small amount of A and B are formed, that this reaction could well be modeled as first order in A. And in this case, the mass balance over a slice of the liquid from Z to Z plus delta Z would give the following expression: the change in the flux with respect to Z plus Kc A would equal 0, where K is the reaction rate constant. That is, any difference between the flux in A going from Z to Z plus delta Z in this liquid is due to the fact that A is being consumed by chemical reaction. So this is basically saying that the net rate of accumulation of the difference between the amount of A coming into a thin slice between Z and Z plus delta Z becoming in and out of that slice is equal to the amount of A that's consumed by chemical reaction. And we can put this together with the mass flux expression to get the following result. If A is sparingly soluble in B, that is, the concentration of A is low. If you think about one gaseous component like CO2 dissolving in a liquid, very often this is the case. The mole fraction of A may be low, and so the second term will be negligible, and the flux of A is just given by the simple expression shown at the bottom of the page. We can now combine that flux expression with the mass balance. We also make the assumption that the total molar concentration is a constant, and this is also a good approximation if the concentration of A and AB are low. The number of moles, total molar concentration, is not changing nearly as rapidly with position here as the concentration of A. And so we can put this flux law into the mass balance to get the expression that's shown here. I've assumed that the diffusion coefficient is constant, which in liquids is often a reasonable assumption. You could relax that assumption, but the solution to the problem becomes more difficult. And the boundary conditions here are that Z equals 0 at the gas-liquid interface. The concentration of A is equal to Ca0. That's the equilibrium concentration of A dissolved into liquid B. And that at Z equal to L at the bottom of this tank, there is no transfer of A through the bottom of the tank, or the flux of A is equal to 0. And since the flux of A is given by minus the diffusion coefficient times the concentration gradient, if the flux of A is 0 at the bottom of the tank, that means that this concentration gradient is 0 at the bottom of that tank. So those are our boundary conditions on the differential equation. It's historically typical to make this equation dimensionless, and we do that by defining the dimensionless concentration in the liquid solution. That's the concentration of A at any point in the solution divided by its concentration at the gas-liquid interface, which is the highest value concentration in this system. So gamma here will always be less than 1. We'll make the z dimension dimensionless by the depth of the tank. And if you put those variables into the differential equation, you'll have a dimensionless number that falls out of this, which we'll call phi, and the resulting differential equation is written as shown in the middle of the page. Phi then is the so-called Thiele modulus, and it characterizes the relative diffusion time scale to the reaction time scale in this liquid system. You'll remember the units on diffusion coefficients are, for example, centimeters squared per second, and so L squared divided by the diffusion coefficient is basically the characteristic time for gas A to diffuse a distance L through this tank. And so this Thiele modulus characterizes the time scale for diffusion relative to the time scale for reaction. Or I should say I got it, yeah, that's right. It's the time scale for diffusion divided by the time scale for reaction. If the reaction is very fast relative to diffusion, then the Thiele modulus is going to be large, and vice versa. The boundary conditions that are made dimensionless are shown here as well. If we solve that equation, the result is shown here. It's just written in terms of hyperbolic functions. And I can go back to the dimensional variables of concentration, thickness, and diffusion coefficient as shown here to get the concentration distribution. And I'll plot that on the next page. As a function, I'll plot the concentration relative to its maximum value at the top or at the gas-liquid interface as a function of position away from the gas-liquid interface. And we'll do this for 3 different values of phi. And so phi, remember, is the Thiele modulus. And if this value is low, that means that the rate of chemical reaction is low. This is we're solving this problem in the limit of pseudo-steady state. And you can imagine what the situation would be if K were 0. So what would the concentration profile look like through the depth of that liquid if there were no chemical reaction? It would be a straight line across the top here. There would be no change in the concentration of A throughout the depth of that liquid. And so if the reaction is slow or non-existent, then this concentration profile is flat. As that reaction gets faster and faster and faster, you see the interplay between diffusion and reaction as the concentration of A decreases as you go deeper into the liquid. And eventually, at high enough rate of reaction, essentially the concentration of A will go to 0 before you ever get to the bottom of the tank. And I point this out because we're going to use this result in a problem that's coming up in just a few minutes. So that's the general form of the solution to this equation. It's also not unusual here to calculate the average concentration of A in that liquid because this is something that could also fit into be used to calculate the total amount of A that's consumed. And if you just integrate the concentration profile over the thickness of the liquid, you get this result for the concentration, average concentration of A relative to its concentration at the gas-liquid interface. That function is plotted here in the graph on the right. And at high values of the Thiele modulus, that is at fast reaction rates, this average concentration goes as 1 upon the Thiele modulus. And that's what gives you this characteristic shape to this particular curve. And as that Thiele modulus gets higher, as the reaction gets faster, then the average concentration of A drops because it's being consumed by chemical reaction. One of the things that is often desired to calculate is how much of A is actually absorbed or by liquid B. And so we'll calculate the flux at the gas-liquid interface, that is at Z is equal 0, by using the flux expression and the concentration profile that we have. The result, if you carry out that calculation, is shown here. And it gives, again, an interesting result. So the prefactor here, Ca0 dAB divided by the liquid thickness L, is again just the result that you would get if the concentration of A were to go from its maximum value, Ca0, to exactly 0 at Z equals L. The flux would be dAB times Ca0 minus 0, the concentration at the bottom, divided by L. So this prefactor is the result that you would get if you were just consuming A at the bottom of this tank, so that its concentration there was 0. Now it's multiplied by a factor that involves the Thiele modulus, and what you can do then is take this concentration, diffusion, and thickness variable and divide it into the flux to get a normalized flux, if you will, as a function of the Thiele modulus. And what it shows is how rapid the flux of A is into the liquid relative to what it would be in this very simple diffusion case. And you can see that at the Thiele modulus equal to 0, that is, if there's no chemical reaction, then there's no flux of A, and so it starts out at 0. And as the Thiele modulus increases, then the flux of A can increase to many times that that you would get just by this simple expression. And that's simply because as the reaction occurs rapidly, then the concentration gradient steepens and the rate of diffusion into that liquid increases, and so you can get fluxes that are much higher than what they would be if the concentration of A didn't go to 0 until the very bottom of the tank. And so now we'll go on to look at, in some senses, an inverse problem and a more practical problem, and that is gas absorption with chemical reaction in an agitated tank. And an agitated tank is one way to envision this. Another step in this process could be that this would be one element of a column, if you will, where absorption is occurring in a countercurrent fashion. And so this could be the local model for a larger model, for example, of an absorber. And so we imagine, in this case, that A, the gas is being sparged into the bottom of the tank. It creates bubbles, and these bubbles then rise through the liquid and leave it at the top. And the bubbles of gas A allow some of the A to diffuse into the liquid B and react. And so we're going to assume, again, the pseudo-binary assumption that the concentration of A and AB in the liquid are small at all times. And additionally, we're not going to let these, at least in the model we have here, the bubbles change size much as they go through the tank. That is, only a little bit of A is taken out of these bubbles on each pass through this device, if you will. And so this is a starting point for other more complex models. So you could imagine that this problem could be quite complex. That there is the fluid mechanics issues to deal with, the mechanism of bubble formation, and so forth. One of the ways to start at this problem is to understand that each of these gas bubbles, as they are lifted by buoyancy through liquid B, each of those gas bubbles will be surrounded by a boundary layer of fluid where the concentration of A goes from its equilibrium value at the gas-liquid interface down to whatever the bulk concentration of A is at any given position in that liquid. And so we will treat the gas bubbles being surrounded by a stagnant liquid film of thickness delta that's small relative to the bubble diameter. And it turns out that this is not an unreasonable assumption for practical purposes. We will also use a quasi-steady concentration profile and assume that this is formed very quickly relative to the lifetime of the bubble in the tank. In other words, that you establish the concentration profile in a very thin boundary layer well before the particle, the bubble gets to the top of the liquid, so that most of the time it's in that tank, it's in the pseudo-steady state region where it's rising through the liquid, and you have essentially a quasi-steady concentration profile around it. Gas A is sparingly soluble in B, and as a result of that, the mole fraction of A in the liquid at any point is going to be taken to be small, and so convective flow in that stagnant film was negligible. And outside of the stagnant film, the concentration of A is going to be given by Ca delta, and we'll assume that this changes very slowly in time. So, in other words, as if you have a fixed amount of liquid in this tank, and you start to bubble A through it, then over time, you could imagine that the concentration of A in the liquid might change. Certainly the concentration of AB would increase with time, but we're going to assume that over the lifetime of one of these bubbles, that is going from the bottom of the tank to the top, that essentially that bubble sees the same concentration of A in the liquid phase, and that stirring helps us quite a bit with that, meet that assumption as well. And so the mass balance and the flux expression are exactly identical to the case we looked at in the previous problem. That is, where you had gas A diffusing into just a tank of liquid B. The results are shown here. Now, the boundary conditions are somewhat different. At Z equals 0 at the gas-liquid interface, Ca is equal to Ca0. And at the edge of the boundary layer surrounding this bubble, the concentration of A now is specified to be this bulk concentration of A outside the boundary layer. So we don't have a flux boundary condition for this second boundary condition. And so the solution to the differential equation looks a little bit different. The concentration profile depends upon the dimensionless depth in the tank, depends upon the Thiele modulus, and depends upon B, the ratio of the concentration of A at the edge of the boundary layer to that at the gas-liquid interface. So B will always be less than 1. And so just to get a look at what these concentration profiles in the boundary layer surrounding one of these bubbles will look like, I've plotted the solution to this equation under the assumption that we have a fairly extreme variation in A, that is that the concentration of A drops to 10% of its equilibrium value as it diffuses through the boundary layer. So this would correspond to a case where the A is virtually all eaten up in that boundary layer. And if the Thiele modulus is low, then the concentration profile approaches a linear concentration profile. And you can imagine that if the Thiele modulus is low, the diffusion is really driving the mass transport in this system, and the flux again. If there were no chemical reaction and the concentration of A were dropping from Ca0 to 1/10 of its value in a planar system going over a distance delta, then you would expect that concentration profile at steady state to be linear. And in fact, when the reaction rate is low, you get towards that linear concentration gradient. The faster the reaction rate is, the more bowed or curved the concentration profile is, and this simply reflects the increased importance of the chemical reaction to increase the driving force, essentially, for mass transfer in the boundary layer. Now, the next slide I'm going to skip over. I always have a hard time remembering the shapes of these hyperbolic functions, so I put this in as a little reminder to me about what those look like, because we see them coming up in a number of these steady state problems. So we can also now start to look at a more complex problem, one in which we calculate the net rate of absorption of A from these bubbles as they go through liquid B. And this starts to, if you think about using this liquid B to absorb A in order to remove it from the gas phase and perhaps clean this gas, this starts to get us at a model of how that would occur. And we're going to do something that is very similar to what we did with Stefan 2 problem, and that is we're going to couple a local scale mass transfer solution together with a global scale solution or macroscopic solution to this problem. So we've just done the local scale or the microscopic scale solution to the mass transfer problem in the boundary layer. And now we're going to couple that with an overall mass balance on the liquid in this tank in order to calculate the total rate of absorption of A. And so the way we'll do that is we'll calculate the flux of A at the edge of the boundary layer on one of these bubbles, and we will multiply that times the surface area of all of the bubbles. So this you might imagine would have the number of bubbles times their surface area, and this will give us then the total amount of A that is being taken away from those bubbles outside of the boundary layer. And we set that equal to the amount of A that is consumed in the liquid by chemical reaction. And that's just the first order rate constant times the concentration of A in the bulk times the volume of liquid. And so we can use the concentration profile we derived previously, and we can calculate this ratio, which I assumed before. I assumed the ratio of Ca delta to Ca0 was 0.1. We can calculate that ratio from this macroscopic mass balance. One of the things that you'll notice in here is the appearance of a ratio of volumes. This is the volume of liquid in the tank, and this is basically the volume of the boundary layer as being an important parameter in determining how fast the concentration falls from the edge of the boundary layer out into from the surface of the gas-liquid interface out into the bulk liquid. Now, you'll also note something that is very important for mass transfer and also for heat transfer is the natural appearance of the surface area per unit volume in this problem. This is the gas bubble surface area. This is the total volume of liquid, and so that enters this expression very naturally. Now, we can calculate the net rate of absorption due to chemical reaction by calculating the flux in this case, at the bubble surface, and I'm going to go ahead and normalize it by the normalization factor that we had before. And you'll see that turns out to give us a normalized flux as shown here, and the result is shown on the right-hand side of this in this equation. If you go to the limit in this result, where the volume of liquid is small relative to the boundary layer volume around the gas, that is, the boundary layer volume becomes very large relative to the total volume of the liquid, then we recover the expression we had earlier for the normalized flux. And I'll go back to that so that you can see where it comes from. That was the result that is shown here, where the flux was simply given for a case where the concentration of A is changing over the entire depth of the liquid. And so you recover that expression in one limiting case here when the volume of the liquid to the total boundary layer volume approaches zero. And I won't belabor this, but you can plot up the solution for this equation as shown here, giving the flux again relative to that very simple result of, what would the flux be if the diffusion occurred through the boundary layer and the concentration of A went from Ca0 to 0 over the distance of the boundary layer. So this normalizes the flux by that result, and you can calculate this as a function of Thiele modulus and also as a function of the ratio of the volume of liquid to the volume of the gas. I'll move on now to a problem that adds an additional feature to the mass transfer that we haven't treated before, and that is what I would call bulk convection or externally driven convective flow. And so in the previous problems we've set the flux equal to minus the concentration, dAB times dXA dZ. That's the diffusion piece. And then we had a convection or frame of reference term, XA times NA plus NBZ. And we have either set that convection term to 0, arguing that XA is small, as in the previous couple of problems, or we have set its value based on the stoichiometry of the chemical reaction at the surface of the catalytic particle, as we did a couple problems, 2 or 3 problems back. Here, the situation is going to be somewhat different. We will have a liquid that is flowing down a column under the influence of a wall of width W and length L, under the influence of gravity, and the velocity of this liquid is really given by the fluid mechanics of the flow of liquid down the edge or the wall of this device. Now, you can imagine that this may not be, in fact, a planar device, but this could be a liquid film that is on the outside of a tube. And if the thickness of the liquid layer is small relative to the diameter of the tube, then you get back to this flat plate analysis. And so we have we're going to have a gas outside of this liquid layer, and the gas will contact liquid B and will absorb into that liquid. Now, in this case, we're simply going to use the case of gas absorption. We're going to turn off the chemical reaction for the time being. And this is very similar. This is very typical involved in things like wetted wall columns for mass transfer. And so we will model the situation where the absorption of A into this liquid B doesn't change the properties of B very much, doesn't change the density, the viscosity of B, the diffusion coefficient of A into B. And this is very often observed when you have a small amount of A absorbing into this liquid. And the basic assumption here is that the mass transfer does not distort the fluid mechanics in the liquid layer. This assumption provides us an important decoupling ability in this problem. We can separate the mass transfer problem from the fluid mechanics problem. Otherwise, if this assumption is not valid, then we have to solve together the mass transfer problem and the fluid mechanics problem. And so we can gain a lot of understanding about the physics of the problem by looking at the simplified version, where we separate the mass transfer problem from the fluid mechanics problem, and the assumption that does that is simply that the absorption of A is sparingly soluble in B, and A doesn't change the properties of B, and therefore the fluid mechanics. And so the fluid mechanics is given by the expression shown here. The velocity in the z direction is given by the maximum velocity, which turns out depends upon the gravitational constant, the density, the viscosity, and the thickness of this liquid layer squared. You can derive this result, and you can see this result derived in the fluid mechanics section of your textbook, so I won't belabor it here. But this will be our expression for the velocity profile of liquid that's moving down, and we will calculate the concentration profile of A inside this liquid layer. Now, if you do a shell mass balance on a small element at x and x plus dx and between z and z plus dz, you will find that when you calculate the amount of A that flows into and out of a given vertical position, as well as into and out of a given position in the x direction, that those all have to add up to 0. And so the change in the flux of component A with respect to z plus the change in the flux of A in the x direction with respect to x has to add up to 0. And what this means is that if you have components that enter, component A that enters this box at x, but doesn't leave at x plus dx, then that amount of A must have gone out in the z direction and vice versa. In other words, this is simply enforcing conservation of mass now over that box between x plus dx and z plus delta z, and that you can imagine that box is of length w here. And so we can, for the z component of the flux, we can write that as shown here using our general flux expression that we've used all along. And we will assume that the flux in the z direction is dominated by the transport of A due to convective flow. That is, that the main mechanism for moving A down this wall is due to convective flow. That diffusion is negligible, and so to first approximation, the flux of A is given by this expression, and that is simply, by definition, it's the molar concentration of A times the molar average velocity. Now, you can do a order of magnitude analysis of these terms, and you can determine under what conditions this is a valid assumption. But under practical gas absorption conditions, this is certainly a reasonable place to start. And what it argues, another way to argue this is that any concentration gradients of XA in the Z direction are likely to be small relative to the concentration gradients of XA in the X direction. Now, we have a problem here, and that is that the flux expression for A in the Z direction, even if we assume convective flow, it's written in terms of the molar average velocity of component A, whereas our fluid mechanics problem is using the mass average velocity. And so you have to go back to the definitions of the mass average and molar average velocities that we discussed very briefly in the beginning of the course, and ask the question of how these two velocities are related. And we're going to talk about this a little bit more when we come into a more, when we get a more detailed and complete set of constitutive equations for mass transfer. But in dilute solution, it turns out that the mass average and molar average velocities are approximately equal to one another. And so we are solving this problem in that limit, and so this gives us a reasonable approximation so that we can put the expression for the velocity from the fluid mechanics into this expression for the flux of A in the Z direction. In the X direction, we have the same expression, and we can write it as shown here. And if we use the expression that the molar mass average velocities are the same, then the expression for the flux of A is given by this expression as a diffusion component and a convection component. Now, the fluid mechanics don't give us any contribution to Vx. The fluid mechanics says that all of the fluid flow is in the Z direction. And so any contribution to the X direction of velocity has to be coming about just due to the diffusion of A into the X direction. And if A is sparingly soluble in B, then this concentration is low, and this term is small relative to the diffusion term. And so the flux of A is given essentially by this diffusive term. Now, I can use these two expressions for the flux of Z, which is convection dominated, and the flux of A, which is diffusion dominated. I can put those back into the mass balance, and I get the expression that's shown here in the middle of the page. That is that the Z velocity times the concentration gradient in the Z direction is equal to diffusion coefficient times the second derivative of C A with respect to X. And I want to to give you a little foreshadowing of how we're going to compare this result in a moment by reminding you that when we had the initial lectures and talked about Fick's second law, talked about the random walk diffusion of dye in a tube as a function of time and position, we used this expression for the mass balance. And I want you to note the similarity between these two expressions. And in fact, the right-hand side of this expression looks very much like the right-hand side of this one. And the left-hand side looks very similar also if you note that the velocity divided by z has units of time. And so the units of vz dca dt are exactly the same as the units of dc dt. And so one way to view this particular problem is to, we speak about, in fact, a characteristic exposure time of the gas with the liquid. And that characteristic exposure time is the distance that the liquid travels, that's L, divided by the maximum velocity. You can imagine that that is the time that the liquid that is sitting at the top edge of this layer, that's the time that that liquid is exposed to the gas for mass transfer to occur, L over V max. But let's get back to solving the problem we were at before. We'll loop back around to this analog with the transient problem in a moment. And so if we put the velocity profile in for the Z component, and the boundary conditions are that at Z equals 0, at the top of this liquid layer, the concentration of A is equal to 0. In many practical situations, you're recycling that liquid, and the concentration may not be 0, but this introduces a trivial change into the final answer. At X equal 0, the concentration of A is equal to its equilibrium partitioning value with the gas that is in the gas phase, so Ca0. And at X equal to delta, the change in the concentration of A with respect to X is equal to 0. In other words, there's no flux of A out the back side of this, into the wall of this column. So the flux at X equal to delta, at the wall surface, the flux of A is equal to 0. That's what this boundary condition says. Now, you can solve this problem analytically, and that has been done. You'll find references to that solution in your textbook. However, very often we are operating these devices in the limit of what is called the short exposure time regime, and this simplifies the solution to the problem. And so the short exposure time limit is given by the following arguments. So if we imagine that this liquid is flowing down the wall of this plate rapidly, such that the exposure time of the gas with the liquid is short, or L over V max is short, then the gas doesn't have time to diffuse very far into the liquid. So the gas is at its highest concentration here at the surface of the liquid, and it starts to diffuse into the liquid, and as the liquid moves down, the gas diffuses further and further, deeper and deeper into the liquid. But in the short exposure limit, the gas never gets very far into that liquid. And this is often the limit in which these kinds of devices operate. And so in this limit, the gas molecules of A that dissolve into B, they never see a velocity that is very different from V max. Remember, this velocity profile is flattest right out here at the liquid surface, and so you don't have a whole lot of change in velocity until you get reasonably deep into the liquid. And so if the gas A doesn't penetrate very far into the liquid, it will never see a velocity that is significantly different from this maximum velocity. So that's one consequence of the short exposure time assumption. Also, if the gas A never diffuses very far into this liquid, we can replace this boundary condition, this no flux boundary condition, at the back edge of this wall. We can replace that with the boundary condition that as x goes to infinity, Ca goes to 0. That is, as you move down into this liquid, the concentration of A drops to 0 or drops to whatever its value was at the top of the column. Now, what we're going to find is that infinity, is not the distance between here and the sun. Infinity can be on the order of microns or fractions of a millimeter, in fact. And so we will replace this boundary condition with this one. That is, that the gas concentration drops off to 0 when you go far enough into the liquid. And so the solution to that, this differential equation with these boundary conditions is shown here. And do you remember the last time that we saw a error function showing up in the solution to a problem? When was that? Sorry? The first homework assignment. And there you weren't solving a steady state problem, right? You were solving a transient problem. And but the solution, I will assert to you, looks very similar to this when we recall that z divided by v max has the units of time, right? And first of all, I just show how the error function changes with the value of its argument. And what you ought to remember here is that the complementary error function changes with the value of its argument. That's the ratio of the concentration at any position to Ca0. Is that when this argument gets to be of order of magnitude 2, this term is 0, or the concentration of A has dropped to 0. So keep that in mind. We're going to come back to that. When this argument gets to be about 2, that the concentration has dropped to 0. This provides us a way at the end of this problem to check whether the solution is valid or not. So let's compare this solution to the solution that we get if we imagine A diffusing from a fixed source at concentration Ca0 out into an infinite bath. And the solution to that problem is very much like the solution to the homework problem, like the solution to the dye diffusing in the tube. It's slightly different, but this one, the solution to this one is analogous to the steady state problem that we've just solved, except here this is an unsteady state problem, and z divided by v is replaced by the time, t. And so again, you see the solution here for the steady state absorption problem in the limit of short absorption times, and here's the solution to the transient problem, and they are in fact identical. And so you ought to think about these problems as being similar in this sense, that there is an analog to the transient problem that is this gas absorption problem. Now, let's get back just a minute to the problem that we were looking at, and so the concentration changes from its maximum value to 0 as this argument u goes up to about 2. And so if we set the value of that argument equal to 2 at the very bottom of this column, you can get an expression for the maximum depth of penetration of the gas into the liquid. And it turns out to be 4 times square root of dABL over B max. Remember, think about this result. And remember the average distance traveled by particles. Remember the mean square displacement laws and things like that. Remember how the mean square displacement of particles scaled with the square root of the diffusion coefficient times time. That's the analog in this particular problem. See how See how the distance traveled scales with the square root of the diffusion coefficient, and in this case, the square root of the contact time of the gas with that liquid. And so the depth of penetration, X max, can be compared then, for example, to the total depth of the liquid film, which is given by the fluid mechanics, and that can provide you a way to understand if this short contact time approximation is valid. We can also look. We can also define look at this argument and see that it has in it basically a ratio of 2 time scales. If we write it in the following form, it's a ratio of a diffusion time scale to a gas-liquid contact time scale. Now, in these particular problems, what you're interested in doing typically is absorbing A into this liquid. You may be trying to take, for example, carbon dioxide out of flue gas. There are some people interested in that here at this university. And so what you'd be interested in doing is calculating the amount of A that you had absorbed into this liquid. And so the way to do that would be to calculate the flux of A at the gas-liquid surface, that is at x equal to 0. From our flux expression for A, it's evaluated as shown here. We can plug in the concentration profile and calculate the flux of A. And you will see that it depends upon Z. That is, as Z increases, the flux goes down. And the reason for this is simply that as you go further down this plate, you lengthen the distance over which the concentration goes from Ca0 down to 0. You basically decrease the concentration gradient, and that slows the flux. So the flux is highest at the top and slows towards the bottom of the liquid film. We can calculate the amount of gas absorbed per unit time in this entire liquid film by estimating this by taking the flux at the boundary and integrating it over the entire length and width of the liquid film, and that result is shown here. And often we would write that in the form that is shown at the bottom of the page. And I want to point out that the width times the factor that appears out front here is the width of the liquid film times the length times the concentration of A in the liquid at the gas-liquid interface. And so you can imagine that the maximum amount of A that you can absorb into that gas film under any conditions is going to be given by this equilibrium, would be given if the liquid contained A entirely at its equilibrium concentration, Ca0. So the maximum amount of A that could possibly be absorbed in a liquid film of this size is Ca0 times L times W times delta, okay? And so this value is the net absorption, or maximum absorption capacity of the liquid per unit thickness of A. And then this factor tells you essentially what is the effective, based on the total amount of gas A absorbed, what is the effective thickness that would correspond to with A being saturated in the liquid. Okay, so this factor will be less than 1, or at most 1 in extreme circumstances. So I'd like to point out again that we show that the net amount of mass transfer is proportional to the square root of the diffusion coefficient, and it's inversely proportional to the square root of the exposure time, L over Vmax over L. And you'll recall that this result is similar expressions where we've had earlier, where the rate of mass transfer depends upon the square root of the diffusion coefficient times time. And so these steady state problems have a transient analog to them. Now, we can take this to another position, and now instead of looking at the gas being transient and the liquid flowing along or the gas basically being in contact with a flowing liquid that's on a flat plate, let's look at how that compares to the situation where you have a bubble of gas A and it is rising through a liquid B. That rising through this liquid B establishes basically a boundary layer, concentration and fluid mechanics boundary layer, at the surface of this particle. And it turns out that the penetration distance of this gas into the liquid is often small relative to the bubble diameter. And this is just due to the fact that the liquid phase diffusion coefficients are slow relative to gas phase diffusion coefficients, and as this bubble rises, you're continuously circulating fresh B past it. And so the rate of absorption of A into this gas is actually determined by the same mechanisms that governs the gas absorption in a falling film. And you can think now the distance over which the gas and liquid are in contact is not the length of the plate, but it's approximately the diameter of this gas bubble. And I'm not going to go into this in extraordinary detail, but I want to bring this up simply because this is a very practical application of gas absorption. It's often occurring out of these bubbles, and I wanted to show you how analogous it was to the gas absorption into that falling film, which is a problem we can treat readily analytically. And so I will just take our falling film result and calculate the basically the amount of mass absorbed per unit time and per unit area. This is in some sense the average flux of A. And so if you write that result this way, this is what you get, and I'm going to compare it with the average flux that is calculated for this rising bubble case. And again, we're not going to walk through that calculation in detail, but look at how similar these are. In the rising bubble case, the velocity is given by the terminal velocity of that bubble, right? That's basically the maximum velocity of the fluid that is flowing past that gas bubble, and the length scale is given by the diameter of the bubble. And so, very often in mass transfer, if you know how to solve one problem that is simpler, like that falling film problem, there's an analogous problem either in the transient problem or, in this case, in the gas bubble. Gas absorption into a rising bubble, from a rising bubble, that is very similar in solution. And so what I want to teach you about here is the structure that these solutions take on. And so even in complex problems, the average flux is dependent on the square root of the diffusion coefficient times effectively the contact time of the gas with the liquid. Now, these are the fine print and the legal notices, if you will, at the bottom of that gas absorption in the rising bubble problem, that it's been approximately confirmed for bubbles that are 0.3 to 0.5 centimeters in diameter, rising through highly purified water. And you'd find a more rigorous example, and this is given in Chapter 20 of your textbook, gives a result that is very, very close to just what you would estimate based upon the falling film result. And this is for a rising bubble in creeping flow. Now, we can turn this problem around and do, in some senses, the opposite problem, and that is the solid dissolution problem, or the diffusion into a falling liquid film, now not from the gas phase, but from a solid that is slightly soluble in that liquid. And so we imagine, again, a liquid flowing down a wall in Newtonian laminar flow, and then there's a section of this wall that is coated with a component A, which is slightly soluble in B and will diffuse out into the liquid and be carried away. And so we will again work this problem like we did with the falling film problem, or with gas absorption in the falling film problem. We'll work it in the limit of short contact time, so that you can see the comparison between the solutions worked under similar conditions. And so if we consider this problem and you analyze the flux of A into the liquid, you get results that are very similar to that we developed for the falling film problem. That is, that the mass transfer of A in the Z direction, that is with the fluid motion, is dominated by convection. The mass transfer of A in the Y direction, that is away from this wall, is dominated by diffusion. The boundary conditions are given by exactly the same ones that basically analogous ones that we had before. At the solid-liquid interface, the concentration of A is its equilibrium partitioning into that liquid, and then out here at Y equals delta, at the edge of the liquid film, we assume that there's essentially no flux of A, that A is not evaporating from the surface, if you will. The velocity profile, again in the absence of mass transfer, is given by this expression. And the problem is a little bit different from the falling film problem, in the sense that the velocity is changing most rapidly near the wall. And so we made the assumption in the falling film problem, where the gas was out here absorbing into the liquid, we made the assumption that the velocity of in the Z direction was essentially Vmax, was essentially constant, that the gas that penetrated into the liquid never really saw very much of a change in the liquid velocity. Now, near the wall, that assumption won't hold, because what's the velocity exactly at the wall? It's zero by the no-slip condition. And so as you move away from that wall, the velocity is increasing. Now, you can argue that in the very beginning, in what we might call the low contact time limit, that velocity increase is essentially linear, and that will be the argument that we will make. And so essentially we'll argue that this concentration of A drops to zero over some time, over some distance that is short relative to the total liquid layer thickness. We will replace the boundary condition at Y equal delta with one that says that as you go out away from that surface, the concentration of A goes to zero. And just next to the surface, we'll say that the velocity, we're in a regime where the velocity changes linearly with distance away from the wall. And I'm going to call that coefficient, or the slope of that change, A, just so I don't have to keep carrying around this group of variables. And so we can solve this problem again in it looks very similar to the problems we've looked at before, except now we have an extra term on the convection side, and it turns out that this the solution to this problem is easiest, at least for me, in terms of a combination of variables approach. And I'll just give you the solution here without dragging you through the mathematical details. But a combination of variables approach, as shown here, gives readily this solution. And so we can calculate the flux at Y equals zero. That's the flux of A away from this surface, how much of A is dissolved into the liquid. Since we have the concentration profile, we have to be a little bit careful now because our concentration profile is written in terms of this transform variable eta, and so we have to do the derivative of the concentration profile in two pieces to make the calculation correctly. But when you do that, you get the result that is shown in the middle. And finally, the result that we're after is the total amount of A that dissolves per unit time in the entire strip of this dissolvable or soluble area of the wall of length L and width W, and that result is shown here, where again these gamma functions are of order unity. And I just want to compare that as we kind of start to wrap this up. I want to write the flux as shown here. If I write that flux in the following way, I've assumed that the concentration of A goes from CA0 down to 0 over some penetration depth that I haven't determined yet. And so if I write the flux as simply using simply this expression, which would have it being a linear concentration profile going from CA0 down to 0, then I can combine these two expressions to get an expression essentially for the penetration depth of this is effectively the penetration depth of A into the fluid, and you see it depends. It has a different dependence on position. What was the dependence on position in the last problem? Yeah, it depended on the concentration was always and the flux was always going according to the square root of velocity over position. And what this is telling you is that in this particular case, the fluid mechanics are exerting an effect on the results you get out, and they're changing the exponent. Actually, let me get this right for you. We'll walk back to the what we call the penetration depth, which was a little earlier, and we saw that the penetration depth scaled as the square root of L over V max, and here the result has that penetration depth scaling with position. So when you get to the bottom of this thing, Z will be equal to L. It has that penetration depth scaling with the diffusion coefficient times L to the 1/3 power. This is foreshadowing a discussion that we'll have when we get to boundary layer theory, that the fluid mechanics will change the dependence, if you will, essentially, of mass transfer coefficients on the Reynolds number. And this is our first sideways glimpse into the effect of fluid mechanics on mass transfer, but this will come up as a recurring theme a little later in the course. And so here are the expressions of for the solid dissolution case that is shown here, and also the gas absorption case for flux, and also for the total amount of material absorbed per unit time and per unit width. And again, what I want you just to take away from this is the change in the dependence of flux on diffusion coefficient and position, and likewise with the net rate of absorption. And the difference in this scaling is due to the difference in the fluid mechanics, whether the gas it's absorbing sees essentially constant velocity, in the case of the gas absorption problem, or whether as it moves out into that liquid it sees a continuously changing velocity. And so I think this is at a good